Hello everyone. Today we are going to discuss sections 5 through 9 in chapter 8. So today we want to begin with exceptions to the octet rule. So there are a number of compounds in which we can draw Lewis structures in which we do not obey the octet rule. So let's start first with compounds in which the atom has fewer than 8 valence electrons, and boron is the best example of that. It is a metalloid in group 3A that has 3 valence electrons, so when it forms bonds, its valence shell has 6 electrons and not 8. So here are some good examples. So this is boron trifluoride, and you can see that the boron has 2, 4, 6 electrons around the central atom, and the same thing over here with boric acid. We've got 2, 4, 6 electrons. So boron has 6 valence electrons around it rather than 8. That makes these compounds actually fairly reactive because, as we know, the octet is very stable. So let's go on to another example. So how about atoms that have more than 8 valence electrons? So these are elements in the third period or higher. So they can form compounds and ions in which the central atom is surrounded by more than 4 pairs of electrons. So let's look at examples here. So there are some examples in our book. So here is shown groups 4A, 5A, 6A, 7A, and 8, even 8, which has a noble gas. Noble gases don't typically react, but under some circumstances we can get them to react. So these compounds are shown in periods 3 and 4. So if we look over here, we can see that silicon has 2, 4, 6, 8, 10 in the SiF5 minus ion, or we can have 2, 4, 6, 8, 10, 12. So again, these are elements that are beyond the third period. So the third and fourth period can expand their octets, and they can be surrounded by 10 or 12 electrons rather than 8. So let's look at an example. Our book authors ask us to draw the structure of ClF4 minus ion. So the first thing we should do is figure out how many valence electrons that it has. So the chlorine has 7, and there are 4 fluorines, and they each have 7, and we have to add the 1 because it's ClF4 minus, and we get a total of 36. So what we do is we figure out what is the central atom. So that's Cl. We can often tell how it is drawn, that the ClF4 minus, that the Cl will be the central atom. So we put 2, 4, 6, 8 electrons, but we have quite a lot more to go because we have 36 in the compound. So what we do is we add electrons around each of the fluorines, and when we do that, we might think that we're finished because you can see that we've obeyed the octet rule around each of the atoms in this compound. But if you count them, we've got 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26, 28, 30, 32 electrons right here, but we need 36 total. So what we have to do is we have to add 2 electron pairs here, and that gives us the 36. So we do that noting that chlorine is in the third period, so it is able to expand its octet and have 2, 4, 6, 8, 10, 12 electrons around it rather than just 8. Now, our book author doesn't ask us to calculate the formal charge, but we should do that anyway. So remember, the way we do that is we split up the electrons. So if I've got 2 electrons here in each of these bonds, then I draw little circles around my atoms right here, and I give 1 electron that's shared to one element and 1 to the other. And you can see if I do this for fluorine, all of the fluorines have 7 electrons around them. And fluorine has 7 valence electrons, so none of those fluorines have a formal charge. But if I look around the chlorine, then I notice that I have 1, 2, 3, 4 electrons. These are one of the electrons that it shares with fluorine, but it has these lone pairs right here, 5, 6, 7, 8. So that means that chlorine normally has 7 valence electrons, but here it has 8. So it has a formal charge of -1. So we can do the math right here. 7 valence electrons is what chlorine normally has. In the structure, it has 8. So that negative charge that's on the ion, that actually resides on the chlorine. All right, what about compounds with odd numbers of electrons? So there are some good examples right here. So these are compounds. They're fairly stable, but they do have an odd number of electrons, which means one of the electrons is going to be unpaired. So these are called free radicals. So a free radical is if you have an unpaired electron. So this compound, if we wanted to draw the Lewis structures, the nitrogen has 5 valence electrons, and each of the oxygens have 6. So that's 17 valence electrons. So when we draw these structures that you see up here on the top, we have 7 valence electrons total, but we also can see that we have not obeyed the octet rule around the nitrogen. We have 1, so we have 2, 4, 6, 7. So we've obeyed the octet rule around each of the oxygens, but not around the nitrogens. But we can't because we have an odd number of electrons. The next thing that we should do, our authors of our textbook don't ask us to do this, but we should calculate the formal charge. So let's do that by sort of splitting up the electrons. So this oxygen has these 2 lone pairs, and let's give them 2 of the electrons that it shares with nitrogen. Let's give this oxygen 1 of the electrons that it shares with the nitrogen. Let's give the nitrogen its single one, plus it gets 2 here and 1 here. So that means we have 1, 2, 3, 4, 5, 6 electrons on the oxygen over here on the left. And oxygen normally has 6 electrons, so this doesn't have a formal charge. But this oxygen does, because we have 1, 2, 3, 4, 5, 6, 7. That's got an extra. So oxygen normally has 6 valence electrons, and now it has 7, so it has an extra one. Over here on the nitrogen has this 1 that belongs to it. So 1, 2, 3, 4. Well, nitrogen normally has 5 valence electrons, so now here it has 1 fewer, so it has a positive charge. So we can do the same pattern over here. Nitrogen has a positive charge, and again, the singly bonded oxygen has a negative charge. So if I do my get rid of my scribbles and do my formulas instead, nitrogen has a positive 1 formal charge, and the singly bonded oxygen has a negative 1 charge. The doubly bonded oxygen doesn't have a formal charge. So this is a neutral compound, and we notice that its formal charges add up to 0. All right, let's go on to molecular shapes. So our next step is to use Lewis structures to predict the 3-dimensional shapes of molecules. And we can do this using a theory called valence shell electron pair repulsion theory, or a VSEPR for short. And the premise of VSEPR is that the electrons in the bonds and in the lone pairs repel each other and seek to be as far apart from each other as possible. So we get something that looks like this, and you might remember when we did our model building exercise a while ago, we looked at some compounds like this. So if we have a central atom and we have 2 groups of electrons, then when they get to be as far apart from each other as possible, that gives you a 180-degree angle and a linear shape. If I have a central atom where I've got 3 areas of electrons, 3 regions of electrons, then they will be trigonal planar. So this is in a plane, and the bond angles are 120 degrees. Tetrahedral, the farthest you can get are to the corners of a tetrahedron. So we have a 3-dimensional shape, and each one of these angles is 109.5 degrees. If I have 5 regions of electron density, right here, I'm going to go above and below, and then to each one of these corners right here. So this is called trigonal bipyramidal. So each one of these shapes is a pyramid. If I have 6 regions, then there's my central atom, and I'm going above, below, and then 1, 2, 3, 4 in this plane. So this is called an octahedron, because if you looked at this shape, the top half has 4 faces and the bottom half has 4 faces. So in this model, none of these central atoms have lone pairs of electrons. So all of the electrons are involved in bonds, but the terminal atoms do most likely have lone pairs of electrons, except if you have hydrogen. So what we want to do when we want to predict molecular shapes is we want to use these steps here. I got this from a different textbook, but it is described in our textbook. So we look at the molecular formula, and then the first thing we do is we draw a Lewis structure. And then what we want to do is we want to count all of the electron regions or all the electron groups around the central atom. So we'll just call it A as the central atom. And then we look at this electron group or electron pair arrangement. And we want to note of positions of any lone pairs or double bonds. We can look at their bond angles. We should count bonding and non-bonding electron groups separately and then come up with a molecular shape. So let's see how we should do this. So let's predict the molecular shape of silicon tetrachloride. So the first thing we do is we draw its Lewis structure. So silicon is in group 4. It has 4 valence electrons. Each of the chlorines have 7, so that's 28. And we have a total of 32 valence electrons. So there's our Lewis structure right there. So we have silicon that's in the middle, and it has, if we count, 1, 2, 3, 4 regions of electron density, or 4 electron group arrangements. There are no lone pairs and no double bonds. It's just all single bonds. So that means that forms the corners of a tetrahedron because we've got these 1, 2, 3, 4 regions. So silicon has the formula AX4, which means we have A, which is its central atom, which is for silicon, is the silicon. Silicon tetrachloride, it's silicon, and the X is the 4 chlorines. So if we build a model of silicon tetrachloride, it's going to look like this. So you'll have the silicon in the center, and you'll have 1, 2, 3, 4 bonds, single bonds to chlorine, and all of those bonds will have a bond angle of 109.5 degrees. So if we look at our Lewis structure and we have compounds that have all bonds and no lone pairs, the electron group arrangement or electron pair arrangement is going to be the same as the molecular shape. So for example, I just gave you an example of silicon tetrachloride. So its electron pair arrangement was tetrahedral, and its molecular shape was also tetrahedral. But if we have central atoms with single bonds and lone pairs, then the electron pair geometry and the molecular geometry or molecular shape are going to be different. So the electron pair geometry depends on the positions of the bonds and the lone pairs, but the molecular shape depends only on the positions of the atoms. So we can look at these examples where if we have a compound like methane, we have a central atom, carbon, and we've got 1, 2, 3, 4. So we have 4 bonds and no lone pairs. So its electron pair arrangement is tetrahedral. And its molecular shape is also tetrahedral. But what if we have something like ammonia? So ammonia has 1, 2, 3 bonds, but then it has this lone pair of electrons. So we still have to count those when we're looking at electron pair arrangement. So we have 1, 2, 3, 4. So those are directed towards the corners of a tetrahedron. So for ammonia, the electron pair arrangement is tetrahedral, but its molecular shape is trigonal pyramidal. So what I like to visualize is, say that you had this very powerful microscope and you could only see the atoms and you couldn't see the electrons. So if you try and visualize just the atoms, then you have this shape right here where you've got a trigonal pyramid right here. What about water? So water has an oxygen and 2 bonds to hydrogen, but it also has these 2 lone pairs. So that's 1, 2, 3, 4 regions of electron density or electron pairs. So this is also tetrahedral, but its shape is either bent or angular. If you look over here, and if I disregard the electrons in terms of contributing to its shape, I have a bent shape right here up at the top. So for this slide, all four of these molecules have the same electron pair arrangement. These all have tetrahedral electron pair arrangements. But the methane has a molecular shape that's also tetrahedral because it has a central atom with 4 bonds. The ammonia is trigonal pyramidal because it has 3 bonds and 1 lone pair. The water is bent or angular because it has 2 bonds and 2 lone pairs. So this is a problem given in our book, and I already went over this for ammonia, but we can do this again. So if we were given an example, we're given a molecular formula. So we're given NH3. So step 1, draw the Lewis structure. So here's the Lewis structure up here. So we draw N, and it has 1, 2, 3 bonds and 1 lone pair. So what we do is we count all the electron groups around the central atom. So we should do that next. So we have 4 of them. We've got 1, 2, 3, 4. So 3 of them are in bonds, and 1 of them is an electron, a lone pair, but we still have 4 groups around the central atom. So the electron group arrangement is tetrahedral. But now we want to note the positions of lone pairs and double bonds. So we find that we have 1, 2, 3 bonds. So if we imagine that we can't see those electrons, then this molecular geometry or molecular shape is trigonal pyramidal. So that's its molecular geometry or molecular shape. The bond angles aren't 109.5. They're more like 107.5. They're a little smaller because of this big electron lone pair kind of pushing all of these hydrogens a little closer together. So this is an example where we have a molecule with 4 regions of electron density around the central atom, but 3 of those are in bonds and 1 is a lone pair. So the molecular shape is trigonal pyramidal. We can do this again for the hydronium ion. So the hydronium ion is H3O+. So again, that's our formula. Let's draw a Lewis structure. So we have oxygen, and then 3 bonds, and then the lone pair. So we have 4 regions of electron density around the central atom. We've got 1, 2, 3, 4. So that means its electron pair geometry, or electron pair arrangement, is tetrahedral. So now we're going to note the positions of lone pairs and double bonds, and we see that we have 1, 2, 3 bonds. So that gives us a molecular geometry or a molecular shape that's trigonal pyramidal. So it's very similar to the NH3 in that regard. Let's do another example. This is an ion ClF2+. So if you draw the Lewis structure, Cl is the central atom, and you've got 2 bonds, 2 fluorines, but you also have some lone pairs. So what do we do next? So we drew the Lewis structure, that's right there. Count all the groups. We've got 1, 2, 3, 4. So that means this is tetrahedral. But now we note the positions of the lone pairs and any double bonds. Well, we only have 2 regions of electron density that are occupied by these atoms. So that means that its molecular geometry is bent or angular. So this has a molecular geometry or a molecular shape that involves 2 bonds and 2 lone pairs. Let's do another example. This is for CO2. So we draw the Lewis structure, is right here. So the Lewis structure, the carbon has double bonds to oxygen. Okay, so we have the molecular formula, we draw the Lewis structure, and we count all the electron groups around the central atom. Well, even those are double bonds, it still just counts as 2 groups. So what that means is that when you have 2 groups, then the farthest they can get away from each other is to be 180 degrees apart. and that gives us a linear shape. So our electron pair arrangement is linear, and because it's two bonds and no lone pairs, our molecular structure, our molecular shape is also linear. So the double bonds here count as one electron group. Here's another example. This is carbonate. So if you go back and look at resonance structures, you should know that this is only one of them, but we can still use this one structure for our example. So molecular formula, CO3 2-. Let's draw the Lewis structure. So the Lewis structure is over here. Let's count all of the electron groups. Well, we've got 1, 2, 3. So again, the double bond counts as just one group. So we have three electron groups. So that means 3 means trigonoplanar. So that means it's a planar molecule, and the bonds are 120 degrees apart. And that's what this looks like. So both its molecular shape and its electron group arrangement are trigonoplanar. So again, we've got 3. I have bonds in quotations because one of them is a double bond, but it still counts as one electron group. So we have sort of 3 bonds and no lone pairs. What about if we have more than 4 valence electron pairs? So these are those exceptions that can expand their octet beyond 8. So here, for these compounds, the electron pair geometry and molecular geometry will be different if they have lone pairs. It will be the same if they don't have any lone pairs. Okay, so let's look at an example. So this is all of these compounds right here all have an electron pair arrangement or electron pair geometry that's trigonal bipyramidal. So if we look at PF3, we have 1 phosphorus and 1, 2, 3, 4, 5 regions of electron density or electron groups. So that means we have the molecular shape for PF5 is also trigonal bipyramidal. But what if we have SF4? Well, if we do the counting, we've got 1, 2, 3, 4, and we've got those electrons right here that are 5. So the electron pair geometry or the electron pair arrangement is still trigonal bipyramidal, but its molecular shape is a seesaw. So I guess this kind of looks like a seesaw or a teeter-totter or whatever you called it wherever in your part of the world. But its shape depends only on the positions of these atoms and not on that electron pair. So that's the molecular shape for SF4. What if we have CLF3? Well, we do still have our 1, 2, 3, 4, 5, which is why we call this trigonal bipyramidal. But 2 of these are in lone pairs. So that means if we just look at the atoms, we have a T-shaped. So the molecular shape for CLF3 is T-shaped. What about if we have xenon difluoride? So again, we've got 1, 2, 3, 4, 5, but 1, 2, 3 of these electron groups are in lone pairs. So if we just look at the shape, it is linear. These are the shapes we have for molecular geometries if you have 6 electron pairs. So this would be 12 electrons around the central atom. So again, an exception to the octet rule. If you have SF6, there's your S, and we've got 1, 2, 3, 4, 5, 6. So that means that its electron pair arrangement or electron pair geometry is octahedral. Its molecular shape is also octahedral. What if we have BRF5? So we have 1, 2, 3, 4, 5, 6. So we classified its molecular geometry as octahedral. But if we just look at the atoms, we have 5 bonds and 1 lone pair. So we get a square pyramid. So we can look over here. So we have a pyramid right here. We have 1, 2, 3, 4. So the base is a square, and then that's our pyramid. So BRF3 has a square pyramidal molecular shape. what if we had something like XeF4? Again, we've got 1, 2, 3, 4, 5, 6. So we have an electron pair geometry or electron pair arrangement that's octahedral. But we have 4 bonds and 2 lone pairs. That makes this square planar. So again, if we're not looking at the electrons, we have 1, 2, 3, 4, and that gives us a square planar shape. So our book authors give us an example to work on, ICl4-. So what do we do first? That's our molecular formula, okay? Then we do the Lewis structure next. So we see that we have iodine is the central atom, and we've got 4 bonds to chlorine, 1, 2, 3, 4, but we also have these 2 lone pairs. So we counted all the electron groups around the central atom, and there are 6 of them. So our electron group arrangement is octahedral. But then we note the positions of lone pairs and double bonds, and we see that we have 1, 2, 3, 4 bonds, and we have the 2 lone pairs. So this is a square planar molecule, and that means the bond angles here will be 90 degrees apart. So this is an example of a compound with 4 bonds and 2 lone pairs, and that gives us a square planar molecular shape or molecular geometry. So if we have compounds with more than one central atom, we follow the same strategy, but we consider each central atom individually. So you might remember doing this when we did our model building example. So if I was going to look at sulfur right here in this compound, I've got 1, 2, 3, 4. So that means its electron pair arrangement is tetrahedral because there are 4. But I've got 2 bonds and 2 lone pairs, so this is going to be bent, and you can see right here that this is bent. Let's go to this carbon right here that's labeled here as carbon 3 in this drawing. We have 1, 2, 3, 4. And we also have 1, 2, 3, 4, no bonds, 4 bonds, no lone pairs. So that has both a molecular shape and an electron pair arrangement that's tetrahedral, and we can see that over here. That's this carbon right here. So we have 1, 2, 3, 4, and that you can see that that shape is tetrahedral. We go to this next carbon that's labeled C2. We could do the same thing. 1, 2, 3, 4. Its electron pair arrangement is tetrahedral, but its molecular shape is also tetrahedral because it's 4 bonds, no lone pairs. So again, over here we have this carbon, which is 1, 2, 3, 4. So you can see in the drawing it's tetrahedral. Let's go here to the nitrogen. The nitrogen has 1, 2, 3, 4. So its electron pair arrangement is tetrahedral, but it's 3 bonds, 1 lone pair. So that means it's trigonal pyramidal, and we can see right here if you look at this nitrogen 1, 2, 3, it's a trigonal pyramidal shape. How about this carbon right here? Well, this carbon has a double bond, so we'll count 1, 2, 3, and if you look at this carbon, you can see that it is trigonal planar, and there's the planar part right there. How about this oxygen? This oxygen has 1, 2, 3, 4, so that means its electron pair arrangement is tetrahedral, but since it has 2 bonds and 2 lone pairs, then it is bent. So what we have to do is we go through the entire molecule and consider each one of these atoms, except for hydrogen. We consider them separately, but we still follow this same strategy. So our book does not have anything like this, but I got this from a different book, and this is really nice because it shows the electron group or electron pair arrangement for 2, 3, 4, 5, and 6 if you have if you have all bonds and no lone pairs. But then for if you've got 3 regions of electron density and 2 of them are bonds and 1 of them is in a pair, you get this bent shape. Here I showed you this before. So tetrahedral, you could have all bonds and no lone pairs, or 3 bonds and 1 lone pair, in which case your shape is trigonal pyramidal, or you could have 2 bonds and 2 lone pairs, in which case your shape is angular or bent. And I showed you this for the trigonal pyramidal too. So all of these have an electron group arrangement of trigonal bipyramidal because they all have 5 regions of electron density around the central atom. But you might have 4 bonds and 1 lone pair, in which case you're a seesaw. You could have 3 bonds and 2 lone pairs, in which case you're T-shaped, or you can have 2 bonds and 3 lone pairs, in which case you're linear. And if you've got 6 regions of electron density, that is your electron pair or electron group arrangement. And if you have all 6 of these are in bonds, then your molecular shape is also octahedral. But if you have 5 bonds and 1 lone pair, then you're square pyramidal. And if you have 4 bonds and 2 lone pairs, you're square planar. So this is a really nice summary of VSEPR theory. So the next thing I want to remind you about, because we did this when we did our model building exercise a long time ago, is electronegativity and bond polarity. But we're in a much better position now, I think, to understand this exercise. So we've been talking about covalent bonding. And there are different types of covalent bonds. We can have pure covalent bonds. So in a pure covalent bond, the shared electrons in the covalent bond are shared either absolutely equally or pretty close. For polar covalent bonds, they are not shared equally. And what happens is that we can predict where the electrons will spend most of their time. They will spend most of their time near the more electronegative atom. So this gives the atoms in that molecule a partial charge. So for example, suppose I give you hydrogen iodide as an example. Well, iodide, the iodine in the hydrogen iodide has a greater electronegativity. So that's why this arrow is drawn in this direction to show that that this bond between them, the electrons aren't really shared equally. Electrons spend more of their time near the iodine because it's more electronegative. So what we do is this is the small Greek letter delta. So we write delta negative to say that there's a partial negative charge because it has more of the electrons are spending their time over there. Whereas for the hydrogen, you have a delta plus or a partial positive charge. So you can denote the bond polarity by drawing an arrow. And we draw the arrow in the direction of where the electrons are spending more of their time. So we can note 3 sort of extreme examples. If we have H2, these are 2 hydrogen atoms in an H2 molecule, and their difference in electronegativity is going to be 0. They're the same atom, so they will absolutely share the electrons very equally. But we have something like HF. I'll show you the table of electronegativities in the next slide, but you have already seen this before. We can look at the difference in electronegativity, and we can see that the fluorine is more electronegative than the hydrogen. So if you imagine that electrons are pink, for example, then this diagram shows that the electrons are spending more of their time with the fluorine. So we have a partial negative charge over here, and this has a partial positive charge. If I was going to draw my arrow, I would draw in that direction. This shows if there's a very extreme difference in electronegativity. So what happens here is that there's no sharing at all. What happened is lithium gave its electron, it just completely gave it away to the fluorine to form fluoride. So that's an ionic compound, and here the electrons aren't shared at all. They're completely transferred, as you'd imagine in an ionic compound. So here is our electronegativity table. So we can see that electronegativity is a periodic trend. So we have increasing as we go across and increasing as we go up. And the way to remember that is fluorine is the most electronegative element. So if you remember that, then you'll remember the electronegativity values. So we have numbers right here we can use for the measurement of electronegativity, and you can use those numbers to figure out the differences. And if you have really huge differences, you're probably going to have an ionic compound. But remember, ionic compounds form between metals and nonmetals because we have the transfer of electrons. Whereas if we're looking with all nonmetals, then we can look at the difference in electronegativity to see whether the bonds are pure covalent or close to pure covalent, or are they polar covalent, in which the electrons are not shared equally. So now that we've discussed electronegativity, that gives us an idea of those formal charges that I keep telling you. So every time you draw a Lewis structure, you should think about formal charges. And last time when we talked about resonance structures, we saw that you can draw lots of different resonance structures for different kinds of ions or compounds. But the other thing that we talked about was that when you mix these together to form the structure, that not all of these structures contribute equally. So in here we can use formal charge to explain that, and we can use electronegativity to explain that too. So this is the at the bottom. These are the Lewis structures for OCN-. This is thiocyanate, and you can draw these three different resonance structures. But once you do that, you should then assign the formal charges. And you see that you can have no formal charge on the nitrogen and no formal charge on the carbon and a -1 formal charge on the oxygen. If you draw instead of a single bond and a triple bond over here, if you just drew two double bonds and then you did the formal charges, you'd find that the -1 formal charge is on the nitrogen. Well, oxygen is more electronegative than nitrogen. So oxygen is really a much happier to have that negative charge than the nitrogen. And here we can see we have a bigger imbalance. If you drew the triple bond over here and the single bond over here, you've got a +1 charge and a -2 formal charge here. So that's got a greater imbalance. So the structure A out of all of those three contributes more to the hybrid mixed structure than the other two. So I want to extend bond polarity to molecular polarity. So we can calculate the bond polarity. In fact, we just did that by looking at the table, looking at electronegativity, and then doing the subtraction. And again, the greater the difference, the more polar the bond, or if it's really, really great, it might be an ionic bond. But in order to determine molecular polarity, we need to determine molecular shape, and we just learned how to do that with VSEPR. So if the molecule has no polar bonds at all, the molecule itself is nonpolar. And the biggest example that you're going to see is hydrocarbons, because the electronegativity of carbon is about the same as the electronegativity of hydrogen. So if you have a compound that's composed just of carbon and just of hydrogen, then this will be a nonpolar molecule. But it's possible for a molecule to have polar bonds, but maybe overall the molecule is nonpolar because the bonds may cancel out. So you might remember doing this about a month ago, but I'll remind you. So if we have something like HCl, HCl definitely has a polar bond between the H and the Cl. And again, the electrons are spending more of their time over with the chlorine because it's more electronegative, so you have a partial negative charge here and a partial positive charge on the hydrogen, and we draw the arrow in the direction of the chlorine. So the way we can demonstrate that this is a polar molecule is you can take the HCl and you can put these in an electric field, and this is off. But when you turn it on, if this is the positive plate over here and the negative plate over here, you can see that all of the molecules line up so that all those partial negatives are attracted toward that positive plate, whereas the partial positive end is attracted to the negative plate. So now we're in a position to figure out whether the molecule has a dipole or not, and this is something that you did with Spartan in your lab work. So for carbon dioxide, you can draw the Lewis structure, and you can see that oxygen has a higher electronegativity than carbon. So you can draw these two arrows to show that, and we have a partial negative charge on the oxygen and a partial positive charge on the carbon. But this molecule does not have a dipole moment because you've got these two arrows and you've got one going east and one going west, and they cancel each other out. So there's no net dipole. So this molecule is considered to be nonpolar. That's different for water because remember, water has a bent shape. So if we have the oxygen here, and oxygen has a greater electronegativity, than hydrogen, so we can draw the arrows like that. Then we've got an arrow pointing northeast and one pointing northwest. So the east and west cancel, but we're mostly going north. So that those dipoles don't cancel each other out. So water is polar, and it does have a net dipole moment, and we can measure that. So I know that our time is short, so I want to just give you a couple quick things for the last section. So that's something called bond order. So that's just a fancy way of saying if you've got a single bond, the bond order is 1. If you've got a double bond, the bond order is 2. If you've got a triple bond, the bond order is 3. The other thing we should note is that single bonds are longer than double bonds, and double bonds are longer than triple bonds. So we should also note that we can have fractional bond orders because in ozone, which we did before, we've got a single bond here and a double bond here, and we have a double bond here and a single bond here. But really, we said that this was a mixture. So really, the bond order here is 1.5 because the bonds between the central oxygen and those two terminal oxygens are somewhere between 1 and 2. So its bond order is 1.5. So it is possible to have bond orders that are fractional. There is a last section of actually calculating enthalpies of reaction using these bond enthalpies, so that I'm going to skip. You can learn that some other time. What I want to leave you is bond enthalpies. It takes more energy to break up triple bonds. So if you go down here, see how these triple bonds, their enthalpies, these are in units of kilojoules per mole. Notice how these bond enthalpies are very high. And for the double bonds, they're also much higher than the single bonds. So these are all single bonds, and they have double bonds and triple bonds. So it takes more energy to break a triple bond than it takes to break a double bond and then to break a single bond. But the other thing I want to leave you with is these are always positive. Notice every single number in this table has a positive value because breaking a bond always requires an input of energy. So please do these problems to assess your mastery of this topic, and I will see you next time.